So welcome to our discussion on the Universal Serial Bus, otherwise known as USB. In today's session, we are going to be walking through the USB architecture, discussing the various terminology, and hopefully demystifying USB. This will be followed by a discussion of the various silicon and software solutions that Texas Instruments has to ease the burden of USB development. Today's agenda will be broken into two different sections. The first section will cover USB architecture, including terminology and classes. This will be followed by schematic and layout considerations, different devices TI has to offer for USB support, and finally we will conclude this with discussion on USB development stacks from TI. So if you ask most people what is USB, they're going to come back with a response such as, oh, it's that port that I plug everything into my computer. And it's very vague, but that's exactly the point. USB is intended to mask the difficulties of communication from the end user. The ease of use from a customer point of view is accomplished by a rather flexible protocol. The next set of slides will outline the architecture of the protocol and discuss the various versions of the Universal Serial Bus. When discussing USB, one needs to look at USB as not a single standard, but a group of multiple standards. Most people differentiate between the standards via speed grades. As seen on the screen, I have outlined kind of the common differentiators that most people use to describe USB 1.1 versus 2.0 versus 3.0. In the development of the 3.0 standard, architects not only looked at increased throughput, they also looked at overall power reduction on the bus. So now we'll take a look at USB topology, and this discussion is applicable for both USB 1.1, 2.0, and the 3.0 standards. We'll start with the USB 1.1 and 2.0 bus topology, as these are largely the same. As depicted by the figure on the right of the screen, the physical interconnect for a USB 1.1 and 2.0 bus is what's known as a tiered star topology. As you can see, the host/integrated hub is always at the center of each USB bus. Devices are connected to each other via a point-to-point connection between host, hub, and device. The tiered star topology allows for up to 7 different layers, with the first layer being the host, and the last layer being a function. This allows for up to 127 unique devices to be present on any given USB bus at any time. USB 1.1 consists of 4 electrical signals. The first being a plus 5 volt USB power supply. This is commonly referred to as V-bus. The second is a ground return. The remaining signals make up the fully differential data pair. USB 2.0 reuses the same 4 wires as specified in the 1.0 standard. The exception to this is when the on-the-go or OTG supplement of the USB 2.0 standard is used. In this case, a 5th signal, or the ID pin, is also present. USB 3.0 is a dual bus architecture. It consists of dual USB 3.0 and USB 2.0 hosts along with their respective bus operating simultaneously. Note that the tiered star topology is still used between 3.0 and 2.0. From an electrical point of view, USB signals reuse most of the USB 2.0 and 1.1 signals. Again, we see the same plus 5 volt USB power supply, the same ground return, but now, instead of 1 fully differential data pairs, we have 3 pairs. The first is the same D+ and D- that are specified in USB 2.0 and 1.1. The 4 additional wires consist of the SuperSpeed receive and the SuperSpeed transmit wires. These are defined for USB 3.0 transactions only. So now that we've understand the bus topology, we're going to go ahead and shift focus to the USB entities, or the different players on the USB bus. The first entity we're going to discuss is the USB host. As outlined in an earlier slide, there can only be one host on any given USB bus. Developers can choose to implement the USB host as a combination of hardware, firmware, or software. As pointed out, all hosts must have an integrated root hub within the system. USB hosts can be thought of the brains of the bus, which means the USB has quite a bit of responsibilities. USB hosts are always responsible device configuration. This is true on both the USB 2.0 and 3.0 specs. Hosts are also responsible for transaction initiation and flow control. One exception to this is with the 3.0 standard, devices can also initiate transactions. Regardless of who initiates the transaction, the host is responsible for scheduling data transfers on all the devices on the bus. The host is also responsible for power management on the bus. The functionality of a hub changes depending on which standard you are implementing. For USB 2.0 and USB 1.1, hubs rebroadcast all traffic they see on their upstream facing port to further downstream facing ports or to lower tiers. One exception to this is when a USB 2.0 compliant hub is operating with high-speed USB 2.0 devices and full-speed 1.1 devices. In this case, not all traffic is broadcast downstream due to bandwidth concerns. For USB 3.0, packets are only routed to the corresponding device. This includes any subsequent hubs in the link path. Again, the exception is for isocronous timestamp packets. These packets are broadcast to all the devices. The majority of the hub responsibilities remain the same through the USB 2.0 and 3.0 standards. Responsibilities include detecting the attachment and removal of USB devices, collecting device status and activity statistics, supplying power to the attached downstream devices, detection and recovery from bus faults, and power management. USB 3.0 hubs also assist in power management. Finally, we'll conclude with devices. A device is defined as a physical and logical entity that performs a specific function or set of functions. Devices are responsible for package acceptance or rejection, decoding, responding to standard USB requests, providing operating details to the host, supporting additional class-specific requirements, and also support for their various transactions. USB 3.0 devices also have the responsibility of replying to at least the USB 2.0 control transactions. Devices are responsible for maintaining protocol and timing requirements of the USB spec. USB 2.0 and USB 3.0 transactions are mutually exclusive on a 3.0 device. Protruding from the host are additional devices, additional hubs, or a compound device, which is a combination of a device and a hub. USB 2.0 has two different power classes. The first power class is a bus powered. The second power class is self-powered. If an entity is bus powered, it draws all of its operational power from the upstream facing port. By default, this is limited to 100 milliamps. However, an entity can negotiate for up to 500 milliamp current draw. Developers of USB 2.0 hubs are required to supply 100 milliamps to all downstream facing ports by default. For a self-powered entity, the operational power is mainly drawn from a non-bus supply. However, a self-powered entity may choose to draw the 100 milliamps that's allowed from the upstream facing port. USB 3.0 inherits the same USB 2.0 power classes with a couple differences. USB 3.0 budgets for a 50% increase in default current draw, or 150 milliamps, and 80% increase for negotiated current draw, or up to 900 milliamps. These are all specified in 150 milliamp units. USB 3.0 also leads to overall lower bus power by introducing additional low power states. So we're now going to move on into terminology which centers around USB entities. One thing to note here is the following slides will assume a USB 2.0 bus or a USB 1.1 bus. This doesn't mean that the terminologies aren't relevant to USB 3.0, However, we're choosing to limit the scope here since 3.0 assumes you are very familiar with the 2.0 and 1.1 bus terminology. The first terminology I'm going to introduce here is the USB address, and this is very analogous with the I2C address that most of us are already familiar with. USB address represents the unique identification for each entity. The exception, of course, is the host, because there's only one host in the system. The addressing that the USB implements guarantees unique addressing for each device on the bus, and this is done via the host assigning the USB address to the device, meaning that devices do not have an address by default. They have to wait until they are assigned one by the host. The next term that you must be familiar with is USB endpoint. And an endpoint is a logical sink or source of transactions between a host and hub and or device. There are two types of USB endpoints, an in endpoint and an out endpoint. In versus out directionality is always referenced from the USB host point of view, looking out onto the bus. Devices can support any combination of in and out endpoints. The one stipulation is that endpoint 0 in and out is always required, and the reason for this is endpoint 0 is the endpoint that the USB host uses to communicate with the device via enumeration, and as well as provide control transactions to initiate the device as well as control it. USB pipe is an abstract concept that is defined as a direct logical connection between a host and one or more different endpoints of a particular device. There are two basic types of pipes. The first is a message pipe, and the second is a stream pipe. I've included this slide for those of you who are curious about the Endpoint-Pipe Relationship. This is a figure taken directly from the USB specification. This picture shows the concept of pipes or pipe bundles between the host and the physical device. USB descriptors provide a way for a device to inform the host of its attributes. USB 1.1 started with 5 descriptors, which are the device, configuration, interface, endpoint, and string descriptors. However, string descriptors are optional. USB 2.0 appended 2 additional descriptors. When utilizing the high-speed throughput of the USB 2.0 bus, 2 additional descriptors are needed. The first being the device qualifier, and the second being the other speed configuration. The format of all these different descriptors can be found in Chapter 9 of the respective USB standard. For the sake of time, I will refer the reader to the Chapter 9 of the USB spec for a detailed description of all the descriptors. We will now move into USB protocol terminology. Again, our focus here is USB 1.1 and the USB 2.0 standards. USB 3.0 protocol terminology is not defined by this presentation. However, it is available in the 3.0 specification if the user is interested. USB enumeration is nothing more than the process of which the host interrogates all the devices on the bus and gathers their attributes or capabilities, as well as assigns them the USB address we previously discussed. All devices must go through enumeration before their functionality is exposed to the host. USB requests are a mechanism which a host can communicate with a hub or device. USB defines standard requests, which are ultimately agnostic to the end device functionality. USB standard requests in the list below must be supported. I've included the data structure which defines the USB standard request for informational purposes. Again, the user should consult Chapter 9 of the USB specification for the details. Our next term is a USB transfer type, and the USB transfer types make up the bulk of the flexibility of the USB protocol. There are 4 standard types defined by the USB 1.1 spec. These are also inherited in the USB 2.0 spec. The first transfer type is a control transfer, and this transfer is primarily used for device configuration, as well as sending command and status requests from a host to a hub and also devices. The implementation and handling of control transfers is required by every device on the USB bus. Our next transfer type is the bulk transfer type, and the bulk transfers prioritize data integrity over data latency, and they do this with error checking for each packet that's sent across the bus. Examples of when you'd want to use bulk transfers is for transferring documents to printers, scanners, transferring data to storage devices. Isochronous transfers, as opposed to bulk transfers, prioritize data latency over integrity. The final transfer type is the interrupt transfer type, and this is used when periodic transfers are needed from a host to device or vice versa. Next, we will discuss USB packets. Each of the previously discussed transfer types is defined by a specific series of USB packets. There are 4 types of packets defined by the 1.1 and 2.0 spec, the first being the token packet, the second data packet, the third handshake packet, and finally the special packet. Token packets are typically used to inform the device of what type of activity the host is requesting. Data packets are typically used to contain the non-protocol payload of the information passed between a host and the device. However, in certain cases, they may be zero-length packets or contain no data at all. Handshake packets are somewhat analogous to the acknowledge no acknowledge bit in the I2C spec, but they're a little bit more detailed. The final packet is a special packet. This is rarely used in USB, and it really, I'm not going to give it too much attention here because it is not used often. Finally, we discover that USB packets consist of a set of various fields. Below you will see 6 packet fields. The order that these packet fields are in a packet is going to depend on the packet. So now we're going to talk about USB device classes and what a device class is and how you'd use them within the USB specification. A USB class is a classification of a group of devices or interfaces with similar attributes. Classes promote interoperability as well as reliability between various manufacturers of USB hubs and devices. Each USB class has its own unique requirements, which are shared across all the devices which implement the particular class. So I've included this slide to give you an example of the type of different end products which are used for the particular USB classes. On the left-hand side of the screen, we have all the defined USB classes. On the right-hand side are the example end products. One thing to note is the details of the classes are outside the main USB specification and reside in their own individual documents. The appropriate choice of USB class is highly dependent on the intended functionality of the device or the end product. If you find that one of the available USB classes does not satisfy the requirements of your end product, you can choose to implement your own vendor-specific class. These are supported in the USB spec. One thing with vendor-specific classes is that it requires you to write the drivers for both the host and the device. This increases the burden on development time. And with all classes, vendor-specific class must conform to the agnostic characteristics of the USB spec. We will now shift focus from the protocol and topology discussions to move to schematic and layout considerations. From a schematic point of view, there aren't too many gotchas. One thing to note is that the speed of the USB bus is dependent on the pull-up resistance on the differential pairs. For example, if one chooses to implement a low-speed device, they would need a 1.5 kilo ohm pull-up resistor from V-bus to D-. For full speed, the 1.5 kilo ohm resistor is simply moved from the D- to the D+. High-speed devices are unique in that they must first enumerate as a full-speed USB device. Once a high-speed capable device enumerates as a full speed, it can communicate its high-speed capabilities to the host. Since high-speed capable devices operate at different signal voltage levels than a low-speed or full-speed device, one should make sure that the 1.5 kilo ohm pull-up resistor on D+ can be dynamically detached once the device is operating in high-speed mode. For 3.0 capable devices, pull-up resistors must have the capability to dynamically attach or detach the pull-up resistors from V-bus. Now we will talk about the USB ID pin, which is present on on-the-go supplement capable devices. The USB ID pin is used by the on-the-go supplement to allow the device to identify if it should operate as a host or as a device. An OTG capable device determines its host or device functionality by resistance and not logic level. If an OTG capable device is to operate as a device, this pin should be left floating. That is, do not bias it to power and ground with a pull-up or pull-down resistor. The reason for this is pull-ups or pull-downs will not only influence logic level, but they may interfere with the detection of the resistance. For host operation of an OTG capable device, the ID pin should be tied directly to ground with minimal trace impedance. And the reason for this is for a device to detect that it should operate in host, less than 10 ohms resistance is required by the USB specification. I will now move on to layout considerations when using USB. Now note that this is applicable for all speeds, but layout considerations become essential for correct operation of high-speed as well as super-speed devices. The first consideration is signal timing. Now, electrical propagation through copper is not infinitely fast. It's on the order of about 120 picoseconds per inch. So what this means is that the routes for the data plus and data minus lines, as well as the superspeed transmit and receive lines, must match in terms of length or be relatively close. If trace length of the differential pairs is neglected, you may find that it takes a lot longer for one side of the differential pair to arrive than the other, potentially leading to false data latched into the receiver. Developers who are expecting the USB high-speed operation and super-speed operation must also consider signal integrity. The reason for this is that ringing and wave distortion can cause false highs or false lows to be latched into the receive device, and if in extreme cases can also cause receiver damage. The key to reducing ringing in and wave distortion is by using continuous impedance across the entire length of the differential traces. This way we avoid any impedance mismatches and potential reflections to interfere with our signal. Additionally, the D+ and D-, as well as the superspeed transmit and receive differential pairs must also be far enough away from other sources of noise so we avoid crosstalk or contamination. A common misconception is that differential signaling offers noise immunity, and this is definitely true if noise is equally coupled onto both traces. If noise couples onto one trace and not the other, the difference between the voltage levels will be skewed. One way to ensure constant impedance across the entire trace length of both the differential pairs is to reference both of the traces to a plane layer. It's okay for the plane layer to be either power or ground, but traces should never route across plane splits. Another consideration is that the USB on-chip I/O buffer, or the buffer that's part of the integrated circuit, should drive a trace whose impedance provides the right load. Too much trace load may prevent voltages from switching in time. Too little trace loads may lead to voltages that ring, and as stated earlier, may cause false triggering. One thing you may not be aware of is that the need for correct and constant impedance dictates trace width, board layer stack thickness, and stack order. It's best to take the extra time to do the calculations for impedance control to avoid potentially spending weeks debugging a layout issue. If you're interested in reading more about USB board layout and design, the following reference papers are a good place to start. In addition to these, you may wish to check out usb.org to see if additional developer papers have been published. We're now going to move into discussing how you, as developers, can utilize TI's silicon and software offerings to easily aid your development in USB applications. TI has a wealth of USB silicon for developing USB applications. For MCU, we have 8-bit MCUs, 16-bit MCUs, or 32-bit MCUs. Our 8-bit MCUs feature the 8051-based USB controllers with dedicated USB serial interface engines. Some examples of 8-bit MCUs are the TUSB 3200, the TUSB 3410, and the TAS1020B. Note the TAS1020B is specifically designed for streaming USB audio. In the 16-bit space, we have the ultra-low power MSP430, which includes the USB developers package. And finally, developers in the 32-bit space MCUs can utilize the StelarisWare USB library, which is offered for the ARM Cortex-M3. For developers with computationally intensive end products, TI offers ARM and DSP solutions for USB. For Sitara ARM9 and ARM Cortex-A8 MPUs, we offer a wealth of USB software. ARM developers can take advantage of Linux drivers, our Sitaraware USB library, and other open source community projects. For single-core DSP developers, we also offer C6ware USB library, in addition to the JUNGO DSP BIOS real-time operating system USB stack. The JUNGO stack is available for the C674X platforms. TI also offers USB solutions in the C6 Integra ARM plus DSP product line. C6 Integra devices, such as the OMAP L1X devices, can take advantage of the C6ware USB library in addition to the JUNGO DSP BIOS USB stack. In addition, C6 Integra users can also utilize the Linux drivers on the ARM side of the platform. TI also offers USB devices in forms of logic. For example, we have 2.0 compliant ESD protection ICs, along with 2.0 and 3.0 transceivers and multiplexers. Future devices will integrate a USB 3.0 PHY. We will now move into discussion of software stacks that TI provides for USB developers. TI offers free of charge an open source USB stack for both the Sitara ARM-only as well as the C6000 single-core DSP, as well as C6 Integra ARM plus DSP microprocessors. For users guides for both Sitaraware and C6ware, please visit processors.wiki.ti.com. DSP developers can take advantage of the USB BIOS stack, which is written by JUNGO. The JUNGO USB stack is available on OMAP L1X C6 Integra devices, as well as C674X single-core DSP devices. This concludes our session on USB. For additional details about either the software or silicon providings, please visit the TI Engineer to Engineer or E2E online community at e2e.ti.com.